In the remote and mysterious valleys of the universe, where stars glitter against a backdrop of enigmatic night skies, lies a colossal galaxy that forever captivates the gaze of astronomers, dreamers, and storytellers. That galaxy is named Andromeda, and today we embark on a grand journey straight into its heart, to the very center of the galaxy. A captivating adventure, lured by dazzling colors and the promise of new discoveries, begins right now. Andromeda, also known as M31, is our closest galactic neighbor. On a clear night, you can spot it in the sky with the naked eye. It lies about 2.5 million light-years from Earth and has a diameter of roughly 200,000 light-years. While that may seem unbelievably distant, it's actually not the case. Unlike many other galaxies, Andromeda possesses a brilliant halo, a massive glowing cloud made up of stars and thin ionized gas. If we could see this halo without magnification in the visible spectrum, it would appear 3 times larger than the Big Dipper. This immense halo surrounding the Andromeda Galaxy is vast, stretching halfway to the disk of our Milky Way, and in some places even colliding with our own galaxy's halo. Yes, galaxies can be astonishingly close. Let's begin our journey, flying through the spherical component of M31, moving ever closer for a direct view of the galaxy's disk with its distinct spiral arms. However, unlike the Milky Way, Andromeda has a significantly thick galactic disk. According to the standard cosmological model, most galaxies form as a result of mergers or by absorbing smaller satellite galaxies. The evidence of a disturbed, thick disk in Andromeda is a telltale sign of such mergers. By analyzing the spectra of stars of different ages and types, we can calculate their velocity dispersion, that is, how much a given star's speed differs from the average speed of its nearest neighbors. The results are fascinating. The older the stars, the higher their dispersion and velocity. This suggests that younger stars are likely orbiting the center of Andromeda quietly, while stars that have finished their nuclear reactions are hurtling through space at tremendous speeds. Moreover, even for red giant stars in Andromeda, this dispersion is 3 times higher than for stars in the Milky Way. This clearly indicates that the history of galaxy M31 is far more complex and eventful. There are numerous segments of spiral arms within the galaxy's disk. In the inner regions, they stand out primarily due to dust, while in the outer regions, they are marked by giant, supergiant stars and ionized hydrogen regions. M31 contains over 400 globular clusters. Among them, the Mayall 2 G1 cluster is the brightest in the local group, with a mass between 7 and 15 million times that of our Sun, and it is likely the core of a dwarf galaxy destroyed in the past. On average, globular clusters in Andromeda have a higher metallicity compared to those in our Milky Way. Another intriguing fact is that Andromeda hosts star clusters with populations concentrated into 3 age groups, from 100 to 500 million years old, around 5 billion years old, and the third group from 10 to 12 billion years old. In contrast, globular clusters in the Milky Way are almost uniformly old, aged between 10 and 12 billion years, and there are no young clusters at all. The presence of young clusters in Andromeda is likely explained by its voracious appetite, meaning it absorbed irregular galaxies in the past. Additionally, M31 contains clusters with properties intermediate between globular clusters and dwarf spheroidal galaxies, objects with no known analogues yet in the Milky Way. Although their brightness and color resemble typical globular clusters, they differ in their enormous radius, about 30 parsecs. The interstellar medium of Andromeda consists of gas at various temperatures and dust, in quantities sufficient to be observed as dust lanes, partially obscuring light from the northwestern part of the central bulge. More than 700 dust lanes are clearly visible thanks to the high inclination angle of the galactic plane. About 4,000 active star-forming regions of ionized hydrogen are known in Andromeda, along with 26 supernova remnants and 20 other candidates for such objects. Furthermore, over 4,000 planetary nebulae have been identified, with an estimated total of around 8,000 such objects in the galaxy. At least 35,000 variable stars of various types have been discovered in M31, primarily Cepheids, bright stars with a well-defined relationship between their pulsation period and luminosity, allowing us to determine their distance. Most Cepheids here have periods ranging from 5 to 125 days. Other notable types of variable stars include luminous blue variables, RR Lyrae
stars, long-period variables, and R Coronae Borealis stars. On average, about 50 novae erupt in the Andromeda Galaxy each year, with at least 800 such events recorded there. At the same time, the frequency of nova eruptions relative to the galaxy's brightness is quite low compared to other galaxies, which may be related to its low star formation rate. Around 2,000 X-ray sources have also been identified in M31, including X-ray binary systems and supernova remnants, as well as hot white dwarfs with high temperatures. Some sources are observed within the galaxy's globular clusters. The bright globular cluster M31G1 has higher X-ray luminosity than globular clusters in the Milky Way. Another difference between sources in Andromeda and our Milky Way is their strong concentration towards the central region. Currently, only one exoplanet candidate has been detected in M31, provisionally named PA99N2, but there is no doubt that within the Andromeda Galaxy exist millions, even billions of planets orbiting its countless stars. They may possess barren atmospheres, or perhaps host flora, fauna, and other forms of life. The search for planets outside our solar system is extremely challenging because planets themselves do not emit light. All confirmed exoplanets reside within our own Milky Way. But with advances in optical technology and data processing methods, we will be able to discover more planets each year, located in ever more distant corners of the universe. Meanwhile, we have approached the center of Andromeda, known as the bulge, the dense spherical concentration of stars at the galaxy's core, and also the brightest part of its spherical system. This image, captured by a space telescope, shows the central region of the Andromeda Galaxy as crowded as a cosmic bus terminal and incredibly radiant. The bright spot to the right of the center is a cluster of stars around the galaxy's black hole. The scattered blue dots throughout the image are ultra-blue stars that have shed their outer layers early, exposing their extremely hot cores. It's quite possible that many other similarly hot stars in this central part of Andromeda are at earlier stages in their life cycle, but they are currently too faint for us to detect. On our journey across the Andromeda Galaxy, we have come very close to its heart. This image shows the clearest picture ever taken of the galactic core in visible light. A supermassive black hole with a mass over 100 million times that of our Sun resides at the center. The event horizon, the immediate vicinity of the black hole where light can still barely enter, is too small to see, but it lies near the center of a dense cluster of blue stars. At the center of the image, a dense cluster of blue stars is surrounded by a larger double nucleus. The double nucleus of M31 is essentially an elliptical ring of old red stars orbiting the black hole but at a greater distance than the blue stars. When stars are at the farthest point in their orbits, they move more slowly, creating the illusion of a second core. The age of the blue stars surrounding the black hole does not exceed 200 million years, so they must have formed very close to it, as a result of an intense burst of star formation. Blue supergiant stars have lifespans too short to have migrated close to the black hole if they had formed elsewhere. Astronomers are striving to understand how these seemingly young stars could form deep within the terrifying gravitational grip of a black hole and how they managed to survive in such a hostile environment. As we delve into the enigma of the black hole in M31, its colossal size, power, and complexity are gradually revealed, giving us astonishing insights into its incredible role in shaping the cosmic landscape. Its irresistible gravity not only attracts stars, gas, and dust, but forces them into orbits, spiraling toward the event horizon, the invisible boundary from which nothing, not even light, can escape its grasp. As technology advances and our ability to explore the universe expands, the supermassive black hole at the center of the Andromeda Galaxy will become an ever more fascinating subject of scientific study. As we continue to unravel its mysteries, this cosmic wonder will undoubtedly serve as a beacon of knowledge for generations of astronomers and enthusiasts to come. But our goal is to plunge deep into this galaxy's very own black hole. In just a moment, all instruments will vanish from the radar screen. It seems our journey has reached its conclusion. Today, we have traversed the vast expanses of the Andromeda Galaxy, encountering wonders beyond imagination. Supernovae casting surreal light, nebulae swirling like ethereal smoke, newborn stars emerging from their gaseous cradles, and of course, a colossal supermassive black hole playing the lead role in the symphony of cosmic evolution. The journey to the center of Andromeda is only the beginning, and we are ready to chart a new course for the next great adventure and new discoveries. If you enjoyed exploring Andromeda with us today, smash that like button and subscribe for more cosmic adventures. Your support fuels our mission to uncover the universe's greatest wonders. Thanks for watching.